Hello students, welcome to Educate. In previous lecture, we have seen the expression for electric field due to a dipole on its axial position. Today, we will derive the relation for electric field due to dipole on its equatorial position. So, to find the electric field on equatorial position, we can consider that this is dipole whose separation is 2a, this distance is a, this distance is also a. Imagine that this charge is minus q and this is plus q. Now this is point, so this is point where electric field is to be found. Suppose this point is P. This is positive charge, so due to positive charge, field will be directed like this, in this direction, and due to negative charge, field will be directed like this, in this direction. Suppose this distance is r. Here this angle is 90 degree, this angle is theta. So we can find, suppose this point is A, this point is B, and this point is P. So this is E1 and this is E2. So let's find out the magnitude of E1 and E2. So here this distance can be found by using Pythagoras theorem. So we can say that E1, electric field due to charge positive Q, will be equal to Q divided by 4 pi epsilon naught times the distance square. Let's write it as x here for time being, which means you know that it will be equal to r square plus e square. So here I am writing x square and its direction is like this. So here if we make this angle theta, so we can resolve it into components. So this angle is theta, it means this angle will also be theta. So in this direction it will be E1 cos theta, and its one component will be in upward direction, and that will be equal to E1 sin theta. Similarly, we can find E2, its direction is like this. So E2, here I have written just magnitude. So E2 equal to Q upon 4 pi epsilon naught x square. Again, its direction will be like this. So we can say E1 modulus equal to E2 modulus, which is equal to just Q upon 4 pi epsilon naught x square, where x is r square plus a square. It's okay. Now again we resolve E2 into components. So one component will be like this. So it will be E2 cos theta, and another component will be in this direction, that is E2 sin theta. Now as you see that E1 sin theta is oppositely directed to E2 sin theta, and E1 in magnitude is equal to E2 in magnitude. So these two components will get cancelled. So net electric field will be due to cos theta components only. So we can say E equatorial is equal to, here we can write E modulus E1 equal to modulus E2, that is equal to E. So we can say twice of E and cos theta. So twice of E means what? E means this value 2Q divided by 4 pi epsilon naught times x square into cos theta. Here theta is this is base, this is hypotenuse. So hypotenuse we have taken as x, so a upon x. But you know 2qa is a dipole moment, which can be written as P divided by, this will become 4 pi epsilon naught x cube, x and x square, and x cube, here x equal to r square plus a square. So we can write it as P upon 4 pi epsilon naught r square plus a square whole power 3 by 2. Later on, we can do certain approximation and we can neglect the value of a, or we can say that r square is greater than a square. In that case, a square will be removed and then we will get r cube. So if you remember, E axial was twice of P divided by 4 pi epsilon naught r cube. Here E equatorial we have got as P divided by 4 pi epsilon naught r cube. So how are they related? So E axial is double of E equatorial. So this is the relation. Here direction is just opposite, because direction of dipole is taken from negative to positive, and here direction of electric field is in this direction, which is parallel to the dipole axis, but its direction is just opposite. So I think you have understood. Now here there is one question. You are given two charges plus minus 10 microcoulomb are placed 5 millimeter apart. It means these two charges form a dipole. Determine the electric field at a point P on the axis of the dipole 15 centimeter away from its center. So in that case, what you have to do, you will apply the formula of axial point. These are the two charges, separation is given, and you can neglect the length of dipole while doing calculation. Similarly, there is a point here. This is on its equatorial point. So then again you can apply the formula for electric field on the equatorial point of a dipole and you can get the answer. So I'm not doing that. Same calculation is given here. If you wish to see, you can see it. So there is nothing tough as such, you can easily do. Now, next point is, what happens when a dipole is placed in uniform electric field? So suppose electric field is directed like this. And here, if you place any dipole, suppose this is minus q charge here, this separation is 2a, and here there is plus q charge. Then electric field is directed like this. So on positive q charge, force QE will act in this direction. On negative q charge, force QE minus QE will act in this direction. So this will try to rotate this dipole. So here, suppose we draw this line and we draw perpendicular from here. We denote it as A, B and C. So we can calculate what is net force here. Net force here, it is QE and it is minus QE. So it will be 0. So net force is not acting. Now as far as torque is concerned, torque is force on positive charge we take here, force on either charge. So QE into perpendicular distance. Perpendicular distance is AC. So QE times AC. What is AC? This angle is theta. So situation is like this. This is 2a, this is perpendicular, and this angle is theta. So this length will be 2a sine theta. So we can write it here as 2a sine theta. Now, if you remember, dipole moment is q times 2a. So we can write it as p, q times 2a as p. So pe sine theta. This is torque. Now, this is magnitude. In vector term, if you want to write, so you can say it is P cross E. If you want to find out maximum value of torque, in that case, theta must be 90 degree, because at 90 degree sin theta becomes 1. So, torque max will be PE. Now, if field is non-uniform, then what will happen? In that case, net force will not be 0, and also there will be some torque. So, now we are going to study different types of charge distributions. So, suppose charge is distributed along a line, then linear charge density lambda is given by q divided by L, total charge divided by length. Unit will be coulomb per meter. Similarly, if charge is distributed in a area, then here we find out charge density, say sigma, will be equal to q times area, and unit will be coulomb per meter square. And if charge is distributed in given volume, in that case volume charge density will be given by q divided by volume. Unit will be coulomb per meter cube. So there will be three types of charges that charge distributions we will study, and their applications will be used while doing some calculations. So let's see them one by one. Now, here we are going to study about Gauss law. Gauss law is used to calculate total flux. If charge is enclosed inside a body, then what is total flux? So phi is given by charge divided by epsilon naught. It does not depend on the radius of the sphere. If charge is q and you take this much sphere or this much sphere, that does not matter, because it depends on charge only. It does not depend on the body enclosing the charge. Now we are going to see how to derive the relation phi equal to q upon epsilon naught. So for this purpose, we consider this figure. Here there is charge q, and we consider small area vector in this direction. So direction of area vector is this, and electric field is also directed outward because this is positive charge. So what we do, we calculate flux. So phi electric is equal to integration E ds cos theta. Here direction of area vector is this, direction of electric field is same, so theta will be 0 degree. So here we can take E outside and we just write integration ds, and this is cos 0 degree, that is why. What does integration ds indicate? If you remember, integration ds, like integration dx gives x, integration dl gives l, integration ds, if s is surface area, so it will give surface area. So here ds is surface area of the figure, and figure is a sphere that contains charge q. So we can say it is E times surface area of the sphere, that is 4 pi r square. This is phi E. But if you remember, electric field due to charge q at a distance r, E at a distance r will be equal to q divided by 4 pi epsilon naught r square. So if you put this value here, what do you get? So you will get phi E equals q upon 4 pi epsilon naught r square times 4 pi r square. So 4 pi will cancel out, and r square will also cancel out. What will be left? So it will be just q upon epsilon naught. So we have got that total flux through this sphere, if it is enclosing charge q, is equal to q upon epsilon naught. So this is proof of Gauss theorem. I think you have understood it fully. Now let's consider this question. Here, I think it is visible. I'm making it a little larger so that you can see, and then we will try to solve it. It's simple question. The electric field components in figure 1.24 are Ex equal to alpha x power half, Ey and Ez equal to 0. It means electric field is directed along x-axis only, and if we put x equal to 0, then electric field will be 0. It means field starts from here and it is going like this, it is increasing like this because it depends on x. Alpha is given as 800 Newton per Coulomb meter power half. We have to calculate total charge and total flux. So here we can consider this phase and this phase only, because field is directed in this direction only. So when we take E and ds, so only in this surface, what happens? E is in this direction, area vector in this direction, so total flux will be 0. Similarly here flux will be 0. In this phase also it will be 0. In that phase also it will be 0. So only these are the two phases through which flux can be calculated. Now consider first phase. So up to here distance is A. So we have to find out what is the electric field on left face. So electric field on left face EL will be from this formula alpha. So we can write 800 into x power half. Here distance x is A. So A power half. So this is value of electric field on left face. If we find the electric field on the right face, so distance from here to here is just 2A. So E on the right face will be equal to 800 times 2A power half. Now, in order to find flux, if you remember, we need E and A. Here theta is 0 degree. So E we have got, we don't have A. It means we need area. So area of this face, this is Q, whose side is given as A, that is 0.1 meter square. So area will be equal to 0.1 square. So we have got E and A both. Now next thing that we have to consider is the angle. So for this face, n cap is in this direction and electric field is also in this direction. So theta will be 0 degree. So if we find flux phi right, so it will be E right into area. Area is 0.1 square into cos 0 degree. EA cos theta. There is no problem. But if we consider this face, area vector is in this direction, whereas electric field is in this direction. It means theta is 180 degree. So phi left if we consider, so E left times 0.1 square into cos 180 degree. And if you remember, cos 180 degree is minus 1. So this will be negative. E left into 0.1 square. Here A equal to, if we write 0.1, so this will be equal to 800 times 0.2 whole square. Did you understand? Here in place of A we can write the value, or we can do another thing. There is another possibility. If you wish, you can take it out. So it is not whole square, it is 1 by 2. And here also, so I think there is slight confusion in writing, so I am just clearing it. So this is E, this is E into, this is just value of E, and 2A, so this is correct, and this is phi r, so electric field on right side, and then 0.1 square into cos 0 degree, that is correct. There is nothing wrong. And here phi L equal to EL into 0.1 square into cos 180 degree, nothing is wrong, right? Up to here you have understood. And what about EL and what about ER? So let's find out total flux. So we can say total flux phi will be equal to phi R plus phi L. Phi R will be what? Phi R can be found by ER, this much, 800 into 2A. So 2A, that is 2 into, or we can say 0.2 power half into 0.1 square cos 0 degree is 1 minus EL. EL is 800 into here EL will be, we have evaluated 800 into A power half, that is 0.1 power half into cos 180 we have taken into area square, this is 1 half, and area square 0.1 whole square. Now we can simplify. So we will get total electric field, sorry, total flux. And you know that from Gauss theorem we can say that phi equal to Q upon epsilon naught. Our concern is to get charge, so Q will be equal to phi times epsilon naught. We have got the value of phi, and we can multiply it to 8.85 into 10 to the power minus 12, and we can get the value of charge. The same thing is explained here in this diagram. If you see, you will understand electric field on the left face, as I told you, electric field on the right face, and then area of the two faces, and theta, as I told you, for this electric field is directed along this line, and here electric field is directed along this line, but area vector is in this direction. So that is why there is angle of 180 degree here. Here angle is theta. Theta is 0 degree. So this is how we can get the required result. Now there is another question. In the same line, but here the case is different. If you observe the diagram, from here electric field is in this direction. From here electric field is in this direction. So it is simple case. In this case, theta will be 0 for right phase, theta will be 0 for left phase. So you can say if electric field is uniform, if distance between these two phases, this phase of this distance and this distance is same, it means whatever electric flux you will get for this phase, same flux you will get for this phase, and then total value will be double of it. So same thing is done here. If you see the calculation, you will see, but let's read the question first. Question says an electric field is uniform and in the positive x direction for positive x, and uniform with same magnitude but in the negative x direction for negative x. It is given that E is 200 I cap Newton per Coulomb for x equal to 0, and it is negative 200 I cap and Newton per Coulomb for x equal to 0. A right circular cylinder of length 20 centimeter and radius 5 centimeter has its center at the origin and its axis along x-axis, so that one face is at x equal to 10 centimeter and the other is at x equal to minus 10 centimeter. So certainly distances of the face from the origin is same. What is the net outward flux through each flat face? What is the flux through the sides of the cylinder? What is the net outward flux through the cylinder? What is the net charge through the cylinder? So we can further analyze. So here the situation shown. You have to find out net flux in this direction. So in this direction flux you can find by formula. Suppose we write it as pi r. So E times here area will be taken as area of square, just circular portion, say it is pi r square, and theta is 0 degree. So we can find answer from here. And if we consider left face, here again theta is 0 degree because electric field from here to here is directed in this direction and the area vector will also be in this direction. So theta is, so again we will get same flux. Pi left is equal to E times pi r square. Now if we consider here this face, so electric field is in this direction and area vector is perpendicular to it. So when we apply E ds cos theta and we make theta equal to 90 degree, then net result will be 0. So here there is no flux. So total flux, if we want to find out, then we can find the sum and that will get doubled, as I told you earlier also. And then if you want to find out the charge, then you can apply Gauss theorem, and from there you can get Q equal to phi times epsilon naught. So the same thing is done here. If you see the calculation, so you can easily understand. Now application of Gauss law. So here field due to an infinitely long straight uniformly charged wire. So let's see how to calculate. So here this is charged wire and we are imagining that there is a cylinder of height L whose radius is R, which surrounds this charged wire. We have to find out electric field at any point on the surface of this cylinder. So here we can easily calculate. So let's see here at this point what is happening. Electric field is in this direction and area vector will be, since we are taking here circular disc, so it area vector will be like this. So ds you can say it is here, so theta will be 90 degree. So electric flux through this phase will be 0. Similarly, for this phase, electric flux, same situation is there. Electric field will be in this direction, area vector will be in this direction, theta will be 90 degree. So there is no flux. So in these two phases, there won't be any flux. Here, there will be some flux because electric field is in this direction and n cap means area vector is also in this direction. So here theta will be 0 degree. So flux can be calculated. Phi will be equal to E integration E ds cos theta. Now E we can take outside and we just write here ds because theta is 0 degree, and here integration ds represents curved surface area of the cylinder. So E times radius is r and height is l, so 2 pi r l. So this is phi E. But from Gauss law, we know that phi E is q upon l. So we write q upon l, and here this will become E into 2 pi r l. Is it correct? Think. No. It should be what? Is it phi equal to q upon l? No. It should be phi equal to q upon epsilon naught. So when we write q upon epsilon naught, then what do we get? What is our concern? We have to find out the electric field. So we can write E equals q upon epsilon naught times 2 pi r and l. But if you remember, line charge density lambda is given by q upon l. So in place of q upon l, we can write lambda. So E will be equal to lambda divided by 2 pi epsilon naught r. So this is expression for electric field due to a straight wire which is uniformly charged. Thank you, Team Educate.